I'd like to solve a problem we have in this lesson. The problem reads, data on third grade test scores for 225 randomly selected school districts in a western state are given below. Districts were classified by class size. Small classes were defined as less than 20 students per teacher. Large class size was defined as greater than or equal to 20 students per teacher. So here in this table we have the summary results from the different districts, those that had small class sizes, those that had large class sizes. Looks like there were 100 districts that were in the small class size and 125 districts that were in the large class size. The request is to compute a 95% confidence interval for the difference in the population mean test scores for small class and large class size districts. So it asked us for the difference in these population means. So in order to do that, of course, they took these samples to accomplish it. We don't have population means, but we do have sample means here. We're going to use the subscript 1 for small class sizes and the subscript 2 here for large class sizes. And so we'll find the difference of these two. Let's see what we have here. We have 668 minus 650, which gives us, looks like 18 as the observed difference between the two sample means. Now, we're going to take this and develop this into a confidence interval so that we have a range of values rather than just this one number. And so we're going to do a 95% confidence interval as requested. And that's going to determine what our T star is. Our T star is going to be determined by the 95% request and also something called degrees of freedom that we've had to deal with the t-tables. And that's going to be the smaller, when working with two populations, or two samples I should say, the smaller of the first sample minus 1 and the second sample size minus 1. So for our situation, let's see, that's going to be 100 take away 1 and then 125 take away 1. So we've got 99 and 124. So we're going to take the smaller of those two numbers. And so the 99 is the degrees of freedom we're going to use when working with the table to the left. So another thing we need to sort out while working with this table, which is, degrees of freedom is going to help us determine which row we should use. We'll speak about that shortly. Also, we need to know which column we're going to be using. And so for a 95% confidence interval, we want to trap, it's just a rough sketch here, 95% in the center. So that leaves us thinking about what's on the exterior portion of this. This will give us our T star. Okay, and so that means that there's 5% left over, which if I split that evenly, that's 2.5% in each tail, or collectively 5% in both of the tails of this model. So we're interested in finding that as well. So these two pieces of information that I have here, that's highlighted in yellow here, the degrees of freedom, and also this idea of how much percentage we have left over, or how much area we have left over. And I guess we write it in the true sense, not as a percent, but how a lot of these tables are recorded as a probability or an area, 0.025. So let's see what row we should be on. We should be on row 99, ideally. But as we scroll through here, we notice that it starts to jump after number 40. And we don't really have exactly a row 99. It goes from 90 to 100. And we're not gonna leap ahead. We're not gonna go for a larger degree of freedom. We're gonna settle for the best that we can do, which would be 90. And we're gonna use this row, and in a second, I want to figure out which column I should use. So if we go up and look at the column titles, we see area in one tail, excuse me, and then area in two tails. Well, we can kind of see they work together. The area we have in each of our tails is 0.025, and let me just kind of circle this. And also, if you put those together collectively in both tails, that's the 0.05 or 5%. So this is going to be the row we're working in, or pardon me, the column we're working in. We're going to trace down. This is a rather large one of these. I'll have to scroll, keep tracing, until they cross-reference these. And that will give us the T star that we want to use for this problem. So T star in this circumstance is equal to 1.987 is what I circled there. So it's a little different. It's not the 1.96 we're used to using with the Z distribution. This is very specific to the T. It's going to tell us how many standard errors we should march out to the right and left. In this case, it's 1.987 standard errors. So I think we've got a lot of what we need here. You know, as I look at this formula that we're going to use that governs this process, you know, the X bars, the S's, and the N's were all given to us in the table. The thing we had to seek out temporarily here was what this critical value T star would be. So some of this I'm doing by memory. You could always look in the lesson and see where these numbers are coming from here. So let's see what we have here. We have 668 minus 650 plus or minus. Now remember, this is our 1.987 that we just located in our T table. And after that, I need to put this sort of enormous square root here and fill in what else we know. So it's basically two fractions added together. So the standard deviation for the small class size, which was 21 squared as indicated, over the 100 is the size, the number of districts, then 20 squared over 125. So that is certainly what's after the plus or minus is something I want to use a calculator for. Let me pull one up real quick. This is Desmos. So I'm going to type that in, 1. There we are, 98, let's clear that out, start again, 1.987 times the square root of, and I'm going to grab a fraction here, and I'll put 21 squared over 100, and then I'm going to kind of arrow to the right, plus, I'm going to grab another fraction and do 20 squared divided by 125. Now what this is doing, it's multiplying the critical value 1.987 almost 2 times what we call the standard error here. And it's what it's going to give to me is that that multiplication of T star times the square root here is the margin of error. So as I hit enter here, I see that I get 5.481. 5.481, and that's what I'm going to put here. Before I forget it, I should write it. 5.481, that's what that simplifies into. 68 minus 50 here, or 668 minus 650 is 18. And so now we have our two last operations we need to do, which is add and subtract for our lower confidence limit. I'm going to do conf with the abbreviation here. And then we can have our upper confidence limit. So that's the beauty of the plus or minus. It kind of, we can do these calculations with, with in the bigger portions, the longer portions, do them simultaneously. So that gives us 18 minus 5.481. I'm also going to have to accomplish 18 plus 5.481. And if I subtract those two values, I get 12.519. And if I add them, I get 23.481. Now let me write that as a formal confidence interval. So remember, it's parentheses state, so it's 12.519. I'm sure these are points of sorts that you earn on the test. And then 23.481. So that is our confidence interval. It looks a lot worse than it actually is. Once you once you see the formula, you probably get a little nervous and think, oh my, this is going to be a tricky one to do. But quite honestly, once you start putting numbers in, most of which are provided, and simplify slowly, you can come up with a confidence interval. So I went ahead and typed this out because of my poor handwriting. It says we are 95% confident that the difference in the population mean scores of the small class size and large class size districts is between, and then I would put in the 12.519 here and the 23.481. So what I do notice about this before I close out this video is that the interval itself does not contain 0. So when I think about all the possible intervals that could happen, this is saying I'm 95% confident that that true difference does not contain 0, which may indicate to me that somehow these smaller class sizes, right? Because that's the one we used in our first. We did sort of a smaller, as I write it here, minus larger summary statistics as we worked with this, means that, this positive, exclusively positive values I see here tells me that the smaller class sizes seem to have a noticeably higher or significantly higher test scores for their third grade reading and mathematics. So just thought I would leave with that. If you have any questions, feel free to contact me or pop into one of my office hours and we can talk about this further.